Okay. So if you didn't read on the sideboard over there today, we are going to be covering the rest of the trig functions, how to graph them. We're going to look at it actually kind of like in the reverse order than what's on the sideboard there. So we're going to look at secant and cosecant first, then tangent and cotangent. Okay? Okay. The good news is that if you're comfortable with graphing sine and cosine, then you're going to be pretty okay with graphing secant and cosecant too. All right. Tangent and cotangent aren't that bad either. It's just they have a little bit of a different period. Okay. So secant and cosecant are going to have the same kind of period that sine and cosine did. Tangent and cotangent, they'll be a little bit different unto themselves. Okay. All right. So first thing, very important that we remember this. Secant is equal to 1 over what trig function? Cosine. All right? And so what we're going to do today is we're going to graph secant, but we're going to use cosine to do that, help us with that. Okay? And that's what you're going to actually do for all of these. Okay? If it helps. I find that it does. All right, and then cosecant of x is equal to 1 over sine of x. Exactly right. Okay? And so those are the two things we want to remember here before we get into the actual graphing. All right, so let's graph secant of x, which is, in other words, 1 over the cosine of x. Okay? So what I'm going to do is I'm going to graph cosine, and then using the graph of cosine will kind of like help us to figure out what that secant graph is going to look like. Okay, and I'm going to do 2 full periods just to get the full effect of it, you know. Excuse me. So cosine, without any transformations, right? Cosine starts at 0 and goes out to 2 pi. And then another full period, then we go from 2 pi out to 4 pi. Okay, and then I'm also going to mark in a -1 and 1 there just for our help. And of course we need to find our halfway points and our quarter points. So then pi and pi over 2 and 3 pi over 2. And then 3 pi and 5 pi over 2 and 7 pi over 2. Okay, all those things. Now, I'm going to graph the cosine graph in pencil, so that way I can erase it away, so you can see what just the graph of, secant is. But I'm going to graph it, the cosine in pencil first, just so you kind of get an idea of what it looks like and stuff. Okay, so cosine graph. Remember, cosine 0 is 1, so we'll put a little point right there, and then pi over 2 is 0, pi -1, 0, 1, 0, -1, 0, 1. Okay, so it looks like this. Okay, so there's cosine, right? No surprises, 2 full periods there, keeps going, all that jazz. Now, secant, right, is the reciprocal of cosine. So when we do something like, and I'm going to do secant in red here, I'll put it in red. Okay, when we look at like a part of our graph, for example, here at 0. Here at 0, cosine is 1. So then secant at 0 should be the reciprocal of that value, right? So cosine at 0, cosine of 0 is 1, so then secant should be 1 over 1. And what is 1 over 1? 1, right? And so we have the same point right there. All right? So 0, 1 is shared both by cosine and secant, because the reciprocal of 1 is 1. Okay? At pi over 2, cosine is 0. And what's the reciprocal of 0? It does not exist, undefined. So we're going to have a vertical asymptote here. Okay, that's how we're going to represent that undefined value. At pi, okay, at pi, what's cosine of pi? Well, -1, right? What's the reciprocal of -1? -1 still. So this point is also shared by both graphs. At 3 pi over 2, we're back at 0 again, which means the reciprocal will be undefined. So we have another vertical asymptote. And in fact, at all the zeros, we'll have vertical asymptotes. Like that. Okay. At 2 pi, the reciprocal of 1 is going to still be 1. At 3 pi, the reciprocal of 1 is still going to be 1. And at 4 pi, the reciprocal of 1 will still be 1. 3 pi -1 is reciprocal of -1. So we have a bunch of dots and a bunch of vertical asymptotes, right? And so it's how we're supposed to come up with a graph from that. Is it just going to be dots and asymptotes? Well, not quite. Not quite. Right? So let me pick another value that's going to be helpful here that we don't typically use, but just to kind of help us get the picture. So between 0 and pi over 2, a nice value for cosine would be like maybe, well, let's see here. If I pick cosine of pi over 6, what's cosine of pi over 6? Root 3 over 2. And cosine of pi over 6, which is equal to root 3 over 2. Root 3 over 2 is not very easy to graph, so we probably wouldn't want to pick cosine of pi over 6. But let's maybe do cosine of pi over 3, because what's cosine of pi over 3? 1/2. And then, so at cosine, so pi over 3, which is like, a little bit closer to pi over 2, maybe in here, we expect that to be about 1/2. And yeah, that's about halfway there, right? What is the reciprocal of 1/2, though? 2. So at pi over 3, secant's going to be 2, so something like up here. Okay, a little bit harder to see, but if we go in the next kind of interval here between pi over 2 and pi, we can do the pi over 3 reference angle, which is 2 pi over 3. What's cosine 2 pi over 3? -1/2. So the reciprocal, right, could be -2. So like right here, we'll say. Okay, and then between pi and 3 pi over 2, we could use the 4 pi over 3. What's cosine of 4 pi over 3? -1/2 again, and then reciprocal, -2. Okay, so it's a little bit easier to see here. All right, we know from this point we have to connect to this point, and we're going to connect in this way. And from this point, we're going to connect to this point, we're going to connect like that. Okay, and do we ever cross vertical asymptotes with our graphs? So not a vertical asymptote. We actually will never do that. Okay, and so we're going to continue just kind of like approaching it. It's something that's like a bound, and that's what we're going to look like. It's like kind of like a almost like a parabola. I'm hesitant to say that it is a parabola, but it's like a parabola, right? And then yes, it repeats. So you can imagine at 2 pi, the same thing's going to happen, except it's going to be like a smiley face here. You remember this, Reese? Yeah. Yeah. So yeah. Okay, now at the 0, right? We only have half of the wave, and so we're only going to do half of the. But if you want, you can draw like a dotted line to show the other part. Kind of right there. Likewise with 4 pi, right, between some 2, we only have half of the waves, so we're going to do like this half. But you can also, if you want to, use the dotted line and show the rest there if you like. Okay? And then if we erase away that cosine, okay, there's secant. There is secant. Okay? And if we do the same thing in our, I'll just show you here the graphing calculator. So I've got, here's 1 over cosine of x, which is, of course, secant. Excuse me. On my window, I'm going to graph from 0 to 4 pi, so 4 pi. And there it is. Okay, you can see the exact same graph that we've got right there. Okay. So I don't think they're quite parabolic, but they're kind of close. They're close in shape to a parabola. I don't think they're the exact same thing. Close enough, right? Like it. Okay. This is not something that, yeah, but it's like, but believe it or not, they have like different names. So this might not be a parabolic relationship. Just like, for example, if you hold like a piece of string or like a necklace or something like that, and that kind of like U shape that necklace creates, that's not actually parabolic in nature. It's a different kind of relationship between like your x and y variables there. It's called a catenoid, I think, C-A-T-E-N-O-I-D. It's not a parabola. It looks a parabola, but it's not. Yeah, anyway, sorry. Tangential. So cosecant is a similar idea. So it's going to, yeah, very close to it. Yep, exactly right. In fact, so let's examine this, and then we'll see an example with cosecant. I'll do one with some transformations there. But very similar, yeah, same idea. Yep. So what's the domain of this? Is it all real numbers?
No.
No. How do we know?
Because you can't go to certain areas.
Yeah, so for example, what numbers aren't included in our domain here? Pi halves.
You can use that R symbol to do this one.
Yeah, kind of. Yeah, we're going to do something like that. Yep. So we're going to say it's all, if you want to, you can use the real number symbol like that. Okay, all real numbers. And again, what that symbol is, it's two, lines, and then you just draw the capital R over top of it like that. Okay, it's supposed to be like a bold R. So all real numbers except, and so, well, our exceptions, there's an infinite number of exceptions here, right? If we kept going, if we wanted to describe the domain for this entire function, there's an infinite number of exceptions. How do you describe an infinite number of exceptions? Well, you start with one of them. I'll start with pi over 2. And I'm going to put a plus k times, and then from pi over 2 to the next one, what we have to do. Like, how can I get from pi over 2 to the next domain restriction there? Add pi, okay? And then if I wanted to go from pi over 2 to the one after that, I would add 2 pi, or 3 pi, or 4 pi, 5 pi, 6 pi. So we're going to add integer multiples of pi. Likewise, I could subtract pi, okay? And so we're going to add integer multiples of pi. So I'm going to put this plus k pi. I'm going to put a comma here and specify that k is an element, that's what that symbol means, an element of the integers. And in integers, you use a capital Z, but you do 2 bars there in the middle. Okay, like that. Now, this is not something I'm going to expect you to duplicate later, but it's just helpful, okay, symbols and stuff like that, especially if you do plan on going on to study more mathematics. This is a common kind of way to describe, something being an element of a larger set. Okay, set of integers. All right. Whew, that was pretty complex. Is the range going to be that complex? Can we describe the range for this thing? Oh yeah, Joshua, sorry, I didn't see your hand. Yes.
All real numbers except 1 through -1.
Okay, so that is certainly one way to do it. All reals except, and do you include -1 or 1?
Yes.
Can we get to -1 here? We can. So we don't want to exclude -1. Or I guess I see what you're saying. Maybe my wording wasn't right. But for our exceptions, we do not want to accept -1 or 1. We want to include those. So I see. Never mind. Yes. Okay. Alternatively, you could say -infinity to -1 inclusive, union 1 to infinity exclusive, like that. Right? That would also be acceptable too. Okay. The period is still the same, 0 to 2 pi, right? We don't talk so much about amplitude for this, so don't worry too much about that. Okay, I mean, I guess you could kind of stretch them out, but they're still going to have roughly the same shape, so I don't really worry about that too much. Okay, it will change their location though, for example, so instead of being at -1, if it was like a 2 in front of the secant, it would be down at -2 and so on and so forth. That'll adjust, but that'll be accounted for. We don't really talk about amplitude though, because these aren't waves. They repeat, but they're not waves though. Okay, questions on any of that? All right, so we'll do one together here with cosecant, and then we'll move into tangent and cotangent. So let's do cosecant of 2x plus 1. Okay, we're going to graph this. Okay. So now, cosecant of 2x plus 1, all right, we're going to use, well, what's the reciprocal of cosecant? Cosecant is 1 over what? Sine. So we're going to use sorry about that, y equals the sine of 2x plus 1. So we're going to use this and then graph this from it. Okay? So, we're going to put that 2x between the 0 and 2 pi like we normally do. Okay? And then to solve here, what should we do to both sides? Divide by 2, right? So we get 0 less than or equal to x less than or equal to pi. Okay? So, we'll go ahead and graph. That plus 1 means you're going to be, what's that plus 1 going to do? Yeah, shift up 1. I'll do 2 full periods here again, just to get the good picture. So 0, let's say there's, whoops, not 2 pi, Mr. Wade, pi, and we'll go out here to 2 pi. And of course, then once you get pi, you have to do your halfway point, so pi over 2, and then pi over 4, 3 pi over 4, 3 pi over 2, 5 pi over 4, 7 pi over 4. Okay, again, I'm going to use my pencil to graph the sine of 2x plus 1, and then we'll use that to get the cosecant. Okay, so this is all stuff we've been able to do before. No problemo. All right, so let's see here. At 0, so 2 times 0 is 0. Sine of 0 is 0 plus 1 is 1. So at 0, we're at 1. And then pi over 4, we go up. And then pi over 2, 0. 3 pi over 4 at the 0. Pi at the 0. 5 pi over 4 at 2. 3 pi over 2, 0. And so the graph of sine is going to look something like this. I think it keeps going if you like. Okay, now, there's our graph of sine, right? Nothing new there, that's all stuff that we've done before. Now we have to again get our cosecant graphed here. All right. So, where are our vertical asymptotes going to occur? At what values?
1.
Where?
Anywhere
Anywhere where the graph crosses the y value of 1. Yes. Okay, so here is going to be a vertical asymptote. Here. Say again?
How do you just get that number?
That it happens here, you mean?
Yeah.
Okay, well, Joshua, you want to try and explain maybe what you were thinking there?
Well, it was 0 for the last one. So whenever it reaches 0, but it has been shifted up.
Yeah, that's a pretty good way to describe it, I would say. Does it make sense, Cameron?
Yeah.
Yeah. Okay. Everyone else okay with that? Why the vertical asymptotes occur at these particular points? Okay. Because students can get it confused here because especially you're like, well, Mr. Widmeyer, in the past one you said they happen at the zeros. Well, 3 pi over 4, that's a 0. 7 pi over 4, that's a 0. Why aren't they happening at these 2 points? And the idea is, yes, 3 pi over 4 and 7 pi over 4 are zeros for the overall function here, but sine and cosecant here, they're being shifted up 1. So the actual zeros occur here at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Even though they're being shifted up 1, eventually we still have the vertical asymptotes occurring at those points. Okay? And then from that, we can then say, aha, so then here at pi over 4, there's our point. At 3 pi over 4, there's a point. 5 pi over 4, 7 pi over 4. And then just from, again, that pi over 4, we can just kind of like draw our kind of up from there, and then from 3 pi over 4 we can draw down from there. 5 pi over 4 we can kind of draw up from there, like that. 7 pi over 4, draw down from there. Say again?
Always going to start on the point of that.
The peak. Yeah, peaks of the valleys, exactly right. Yep. And they will stay the exact same point. So you share that part, but everything else goes away then. Okay? Some I'm going to erase away. And then voila, there it is. Okay? Just like Liam said earlier, how it kind of just flips a little bit. I mean, it's the same kind of shape almost, it just shifted, right? Because what is sine but a horizontal shift of cosine, or vice versa, right? And so we'd expect the same thing here for secant and cosecant. They're just horizontal shifts of one another. Okay? Nothing too crazy there. All right? Questions on that? So I didn't bother showing you a plain cosecant. I just showed you like a transformed version because, again, it's just using sine and cosine stuff we already know. So, questions on any of that? All right. So, if not, then let me talk to you about tangent and cotangent real quick, and I'll introduce those basic pictures to you, and then I'll get you guys started on your assignments, okay? So we'll talk about tangent first, and then cotangent. Question? And hypercourses, of course, yes. Both of course. Okay, so let's look at tangent and cotangent. Okay, we'll talk about tangent first. So, sine, cosine, secant, and cosecant all have the same period, 0 to 2 pi, right? You start at 0, go to 2 pi, okay, right? Tangent has a unique kind of starting period to itself. Cotangent also has a unique starting period to itself, okay? So in other words, you'll need to have 3 periods memorized, okay? One period that goes to 4 trig functions, right? Sine, cosine, cosecant, and secant is 0 to 2 pi. Tangent's period, okay, it's only pi in length. Tangent repeats every pi, and it's kind of like initial period is from negative pi over 2 to pi over 2. Okay. Excuse me. That is tangent's period. Say again?
What is like the multi-step?
Bx minus c, like for the transformation part, you know. Okay. Tangent's range, negative infinity to infinity. Okay, so tangent has an interesting, you know, kind of different kind of shape to it than sine and cosine. Sine and cosine, their ranges were negative 1 to 1. Tangent has all real numbers as its range. You can get any value with tangent, any y value with tangent, I'll say. The domain is limited, though. And this makes sense, right, because if we think about tangent in terms of sine over cosine, right, if tangent is the same as sine over cosine, we know that cosine can be 0, and so therefore tangent can be undefined sometimes. So we'll say for the domain here, all x except x equals pi over 2 plus k pi. K is an element of the integers. Okay. So it's got the same domain as secant, which makes sense because both secant and tangent have over cosine, right? It's the cosine that is in the denominator for both of those. Okay. So let me show you a little sketch here of tangent. So I'm going to draw my x-axis. Okay. I'm going to draw two full periods for us here. So here we'll say negative pi over 2. Here we'll say pi over 2. So that's the distance of pi, so I'll go pi out more to 3 pi over 2. You only need to find the midpoints. You don't need to find the quarter points here. So from negative pi over 2 to pi over 2, that's one full period, and I find the midpoint there at 0, and then the same thing here, from pi over 2 to 3 pi over 2, the midpoint is pi. Okay, so let's kind of put some of these in, right? So I'll start at, I guess I'll start at negative pi over, no, let's just start at pi over 2, that's easier. So tangent of pi over 2, what is tangent of pi over 2? Well, think in terms of sine over cosine. What's sine of pi over 2? 1 over cosine of pi over 2? 0. 1 over 0, we call that undefined, right? And so vertical asymptote there. Okay. At negative pi over 2, well, what's in the same position on the unit circle as negative pi over 2? Or in other words, what's coterminal to negative pi over 2? 3 pi over 2, 3 pi over 2, 3 pi over 2. Coterminal means they share the same starting point and stopping point, right? So they both end in the same position on the unit circle. Negative pi over 2 is the same as 3 pi over 2. Cosine of 3 pi over 2 is 0. So you're like, the sine of 3 pi over 2 is negative 1. So it's negative 1 over 0, so it's undefined there. Okay? Likewise, 3 pi over 2 also we know is going to be undefined, right? So there it is. What's tangent of 0? Well, what's sine of 0? 0. Cosine of 0? So 0 over 1 is 0. So we have a 0 there at 0. And then at pi, guess what? It's another 0. Okay, and here's what the graph of tangent looks like. And here's, so it looks like a cubic, kind of, but a cubic that repeats. Okay? So there's tangent. Questions on any of that? Okay. And of course, you can do, we don't worry so much about vertical stretches here. So if you throw like a 3 in front of tangent, it's still going to have pretty much the same shape. I'm not going to have you worry about kind of like identifying that. However, if it's negative tangent, what will that do to the graph? Flip it over the x-axis, right? You could also do horizontal stretches and shrinks or shifts, right? You can also shift up and down as well, or vertical shifts and stuff. But there's your basic tangent, okay? I think I'm just going to show you cotangent and then go on from there. If you want additional, you want to see more, I can do that too. But I think you guys get the idea. It's very similar to what we did for sine and cosine. So, in the interest of trying to give you as much time as I can to start homework and get your own practice in, I'll just present this last piece here. Okay, cotangent. Its period is also pi. Its range is also negative infinity to infinity. Okay. Here's the major difference. Its initial period here is from 0 to pi. Okay? So sine, cosine, cosecant, and secant, I can't hold my pinky down, those 4 all have a period from 0 to 2 pi. Tangent, negative pi over 2 to pi over 2, cotangent, 0 to pi. You have to have those 3 memorized and associated with the right trig functions. Okay? The domain, all x except x equals k pi. K is an element of the integers. Okay? Which is the same domain as cosecant. Okay? And so it will have a similar graph to tangents. Zero to pi, so there's 0, there's pi right there, we'll say, and then I'll go out to here to, like, say 2 pi right there. Again, you only need to find the halfway points. And in fact, now that we have tangent up there already, cotangent is that much easier. So for example, here at 0, right? Tangent of 0 was what? What's the reciprocal of 0? Undefined. So we have an asymptote at 0. Okay? The reciprocal of undefined at pi over 2, well, that's like 1 over 0, right? The reciprocal of that would be 0, right? And so at pi over 2, we have a 0. And then at pi, asymptote. 3 pi over 2, 0. 2 pi, asymptote.
Just the same graph.
Close. So, the other thing we have to think about here is that, for example, between 0 and pi over 2, we're going from very small numbers up to infinity. If you reciprocate that, the reciprocal of a very small number is now a very large number, right? If you take like 1/3 or 1/4 or 1/5, you know, smaller and smaller and smaller, closer to 0, reciprocate those are large, right? Whereas you take a really large number like a million, a billion, a trillion, reciprocate those, now they're going to be very small. So what you're going to see here is very large numbers going down to very small numbers like this, and then very large negative numbers going down to very small, very large negative numbers like that. And so it's the, you know, kind of like, oh, I'm off the screen, my bad. There you go. So they kind of go down from left to right, and that creates that. Okay? So there's cotangent, again, with all the transformations and things like that. Okay? Questions on any of that? All right, so I'm going to give you your assignment then. It's going to be up here, just a sec. Yes? Yes. Thanks for sharing that. Son of a gun, it stopped again. Good luck, Claire. Yes. That's frustrating. Frustrating. Yes, I'll get those back in just a moment. Wait for the homework up. Okay, your homework is page 337.
15, 21, 27, 35.
Whoops, 27. Yes, that's right. Okay. Homework is on the board. You're off. Okay.